The base of a solid is the region enclosed by the graphs of y is equal to negative x squared plus 6x minus 1 and y is equal to 4. Cross-sections of the solid perpendicular to the x-axis are rectangles whose height is x. Express the volume of the solid with a definite integral. So pause this video and see if you can have a go at that. All right, now what's interesting about this is they've just given us the equations for the graphs, but we haven't visualized them yet. And we need to visualize them, or at least I like to visualize them, so I can think about this region that they're talking about. So maybe a first thing to do is think about, well, where do these two lines intersect? So when do we have the same y value? Or another way to think about it is, when does this thing equal 4? So if we set them equal to each other, we have negative x squared plus 6x minus 1 is equal to 4. This will give us the x values where these two lines intersect. And so we will get, if we want to solve for x, we can subtract 4 from both sides. Negative x squared plus 6x minus 5 is equal to 0. We can multiply both sides by negative 1. We will get x squared minus 6x plus 5 is equal to 0. And then this is pretty straightforward to factor. 1 times 5 is 5, or actually I say negative 1 times negative 5 is 5, and negative 1 plus negative 5 is negative 6. So it's going to be x minus 1 times x minus 5 is equal to 0. And so these intersect when x is equal to 1 or x is equal to 5. Since we have a negative out front of the second degree term right over here, we know it's going to be a downward opening parabola, and we know that we intersect y equals 4 when x is equal to 1 and x equals 5. And so the vertex must be right in between them. So the vertex is going to be at x equals 3. So let's actually visualize this a little bit. So it's going to look something like this. I'll draw it with some perspective because we're going to have to think about a three-dimensional shape. So that's our y-axis. This is our x-axis. And let me draw some y values. So 1, 2, 3, 4, 5, 6, 7, 8. This is probably sufficient. Now we have y is equal to 4, which is going to look something like this. So that is y is equal to 4. And then we have y is equal to negative x squared plus 6x minus 1, which we know intersects y equals 4 at x equals 1 or x equals 5. So let's see, 1, 2, 3, 4, 5. So x equals 1, so we have that point right over there, 1 comma 4, and then we have 5 comma 4. And then we know the vertex is when x is equal to 3, so it might look something like this. We could substitute 3 back in here, so let's see, y will equal to negative 9, 3 squared, plus 18 minus 1. And so what is that going to be? That's going to be y is going to be equal to 8. So we have the point 3 comma 8. So this is 5, 6, 7, 8. Yep, right about there. And so we are dealing with a situation. We're dealing with a situation that looks something like this. This is the region in question. So that's going to be the base of our solid. And they say cross-sections of the solid perpendicular to the x-axis. So let me draw one of those cross-sections. So this is a cross-section perpendicular to the x-axis. Are rectangles whose height is x. So this is going to have height x right over here. Height x. Now what is this, the width, I guess we could say, of this rectangle? Well, it's going to be the difference between these two functions. It's going to be this upper function minus this lower function. So it's going to be, that right over there is going to be negative x squared plus 6x minus 1, and then minus 4, minus the lower function. So that could be simplified as negative x squared plus 6x minus 5. And so if we want to figure out the volume of this little section right over here, we'd multiply x times this, and then we would multiply that times an infinitesimally small depth, a dx. And then we can just integrate from x equals 1 to x equals 5. So let's do that. The volume of just this little slice over here is going to be the base, which is negative x squared plus 6x minus 5, times the height, times x times the depth times dx. And then what we want to do is we want to sum up all of these. And so you could imagine right over here you would have, or like right over here, you would have a cross-section that looks like this. X is now much larger. The height is x. So now it looks something like this. So I'm just drawing two cross-sections just so you get the idea. So these are this is any one cross-section for a given x. But now we want to integrate. Our x is going from x equals 1 to x equals 5. X equals 1 to x equals 5. And there you have it. We have expressed the volume of that solid as a definite integral. And it's worth noting that this definite integral, if you distribute this x, if you multiply it by all of these terms, it's very solvable. You don't need or it's very solvable without a calculator. You're just going to get a polynomial over here that you have to take the antiderivative of in order to evaluate the definite integral.